The vessel arrives before dawn. You hear it before you see it, a low, rhythmic concussion, felt more in the chest than in the ears, rolling across open water from somewhere out in the gray. Then you spot it, a jack-up installation barge, its 4 steel legs planted on the seabed, holding the whole platform steady above the chop as though the North Sea has simply agreed to keep still. Hanging beneath a crane arm the height of a 10-story building is a steel tube. Not a pipe. A monopile. 10 meters in diameter. Roughly 80 meters long. Weighing somewhere in the region of 1,300 tons. They are about to drive it into the ocean floor like a nail into softwood, using a hydraulic hammer that strikes with a force of 3,000 kilojoules per blow. And they will do this until 40 meters of that steel tube has disappeared entirely beneath the seabed. The question nobody standing on that barge stops to ask, because they already know the answer, is, why so deep? That question turns out to be far stranger than it sounds. When most people imagine an offshore wind turbine foundation, they picture something like a pier or a dock piling. A post in the ground. Something that simply needs to be heavy enough not to float away. That instinct is wrong in almost every important way. The 40 meters is not about weight. It is not about preventing the turbine from sinking or drifting. It is about a force that most people never think about when they look at a wind turbine, the overturning moment. Here is the actual trick, and once you understand it, you will see it everywhere. A wind turbine is not a column under compression. It is a lever. A very tall, very heavy lever, with the wind pushing horizontally near the top and the ocean fighting to push back at the bottom. The Siemens Gamesa SG-15-236, one of the largest offshore wind turbines currently in service, carries a rotor that sweeps a circle 236 meters across. Its hub sits roughly 150 meters above the waterline. When that rotor is generating 15 megawatts in a full gale, the horizontal thrust load at the hub can exceed 8,000 kilonewtons. Add the wave loading pushing against the tower at the waterline, waves that may be 8 or 10 meters tall in the North Sea, and the combined overturning moment at the foundation level reaches roughly 20,000 kilonewton meters. That is the number that drives every other decision on this project. Think of it this way. Imagine pressing your hand flat against the top of a flagpole and pushing sideways. The harder you push at the top, the more the base of the pole wants to pivot and lift on one side. The foundation must resist that pivoting. It must clamp the bottom of the lever so firmly into the earth that the lever cannot rotate. That clamping force comes entirely from the soil gripping the outside of the steel pile. And the only way to get enough grip is depth. The soil mechanics behind this are precise and counterintuitive. At the surface of the seabed, marine sediments are relatively loose. Sand and silted clay have low lateral resistance, they shear away under sideways pressure without much fight. But as you go deeper, the weight of all the sediment above increases what engineers call the effective overburden pressure. That pressure compresses the grains together and dramatically increases their passive resistance against a pile being pushed sideways. A pile embedded 40 meters fine soil that is resisting it perhaps 8 to 12 times more effectively than the soil at 5 meters. The load is not carried by the tip of the pile. It is carried along the whole embedded length, with the deepest portion doing the heaviest work. If you shorten the pile to 20 meters, you would not simply have the resistance. You would reduce it by far more than half, because you would be losing precisely the deep, high-pressure soil that provides the foundation's backbone. This is where the engineers encountered the first open loop. When monopiles were designed for the smaller turbines of the early 2000s, machines of 2 or 3 megawatts with rotor diameters below 100 meters, pile diameters of 4 to 5 meters and penetration depths of 20 to 25 meters were adequate. The overturning moments were manageable. But as the industry moved to 5 megawatts, then 8, then 15, the turbines grew taller and the rotors grew enormous. The overturning moment does not scale linearly with rotor size. It escalates dramatically, because thrust force scales with swept area and the lever arm grows with hub height simultaneously. A 15 megawatt turbine generates an overturning moment roughly 6 to 8 times greater than a 3 megawatt turbine, even though it is only 5 times the rated power. The pile had to grow in both diameter and depth, and the engineering had to rethink nearly everything. A 10-meter monopile is not simply a bigger version of a 5-meter one. It introduces structural behaviors that smaller piles do not exhibit. At that diameter, the pile wall, which is typically between 90 and 120 millimeters of rolled steel, behaves almost like a thin-walled cylinder, and becomes vulnerable to a failure mode called ovalization, where the cross-section deforms under the hammering process. The hydraulic hammers used to install these piles, machines like the IHC Hydrohammer S3000, which delivers up to 3,000 kilojoules per strike, must be carefully tuned in blow rate and energy per strike to drive the pile without inducing enough local stress at the pile head to crack or deform it. Each hammer blow sends a compression wave down the full length of the steel at roughly 5,000 meters per second. Engineers monitor the response of that wave in real time using sensors at the pile head, a technique called pile driving analysis, to understand exactly how the soil is responding and whether the pile is at risk of damage before it has even finished installation. Now for the false belief that almost everyone carries. Most people, if they thought about it at all, would assume the 40-meter depth is chosen to resist the single largest storm, the once-in-50 years hurricane-level event. Protect against the worst case and you are done. Engineers do not primarily design offshore foundations for that single worst event. They design them for fatigue. Over a 25-year operational life, the foundation of a large offshore turbine experiences roughly 100 million load cycles. Every rotation of the rotor creates a load cycle. Every wave that passes the tower creates a load cycle. The amplitude of each individual cycle may be far below the material's ultimate strength, but repeated cycling degrades steel and degrades the soil-pile interface through a process called cyclic degradation. The soil grains around the pile rearrange themselves under oscillating pressure, and if this is not accounted for, the pile can slowly work itself loose, not all at once, but incrementally, millimeter by millimeter over years. The foundation depth and the pile stiffness must be calibrated so that the natural resonant frequency of the whole turbine-tower-foundation system does not fall within the frequency band of wave energy or rotor excitation, otherwise the structure would be driven toward resonance, amplifying every small load into a much larger structural stress. The pile's role in setting that resonant frequency is primary. Which of these engineering constraints would you most want to understand better, soil fatigue, resonance, or the hydraulic hammer dynamics? Tell me below. But there is one more layer, and this is where the story becomes genuinely surprising. Even a perfectly designed pile, driven to the ideal depth, can be undermined by a process happening continuously at the seabed surface, scour. Ocean currents accelerating around the base of the pile erode the seabed sediment in a ring around the structure. Left unchecked, scour can remove 2 to 3 meters of sediment from around the pile over a single winter storm season. That may sound modest, but losing 2 meters of effective embedment depth from the top of the pile's soil engagement removes the portion of the soil with the lowest resistance, and more importantly, it changes the effective lever arm geometry, shifting where the soil reactions are concentrated. Engineers account for this by surrounding the pile base with a skirt of rock armor, crushed granite or basalt in carefully graded layers, that disrupts the current acceleration and protects the seabed. The target penetration depth of 40 meters is itself calculated assuming a defined scour depth has already occurred. The 40 meters is the depth after the worst expected scour. Without the rock armor, the required installation depth would be even greater. This is what the vessel in the gray dawn is actually accomplishing, blow by slow blow. It is not simply pushing a very large steel post into the ground. It is calibrating a resonant frequency. It is pre-accounting for soil that will erode before it is ever seen eroding. It is embedding a structure that must survive 100 million load cycles without a single interval for maintenance below the waterline. The depth is not a safety margin chosen conservatively. It is the precise minimum value demanded by the physics of levers, the mechanics of cyclic soil behavior, and the mathematics of structural resonance acting together over a quarter century of open ocean weather. Every time you see a turbine standing in offshore water, what you are actually seeing is the top 3/4 of the engineering. The part that matters most is invisible, buried in the dark below the sediment, held in compression by gravel and pressure and careful calculation. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering.